Hello, this is Ms. Martinez. In this video, we are looking at infinite limits and limits at infinity. Those might sound like the same thing, but by the end of this video, you're going to see that they are really quite different ideas and statements. So let's get started. As a student, I'm looking for you to be able to compare and contrast infinite limits and limits at infinity, to use properties of infinite limits to find asymptotes and describe function behavior, and lastly to use relative rates of growth of power, logarithmic, and exponential functions to analyze limits. Throughout this unit, you all have come across two different types of scenarios, and we're going to compare and contrast them in this section. You've looked at the behavior of functions as they approach infinity, as well as functions that are tending toward infinity. So let's begin and look here. The f function is on top and the g function is on the bottom, and we're going to define what an infinite limit is. An infinite limit is any limit such that as x approaches a, and it's resulting in infinity or negative infinity, a being a real number. So it's any limit where x is approaching a, which results in infinity or negative infinity. So looking at your f function, as you approach 4 from the left, the limit as x is approaching 4 is infinity. Coming from the right, it is going towards negative infinity, though that is a scenario where you have an infinite limit. In your g function, this occurs at 1. As you approach 1 from the left for your g function, it's going down to negative infinity. And as you approach 1 from the right, it is tending towards, it's approaching infinity. So when you have an infinite limit, that is going to result in a vertical asymptote at that particular x value, x being your a value, the place where your graphs are going to infinity or to negative infinity. Now let's contrast that with a limit at infinity. A limit at infinity is a limit where your x is going to infinity or your x is going to negative infinity. Looking at your f function here, as x goes towards negative infinity, the limit is actually negative 2. And it is the same when you're going to positive infinity. It is, again, for your f function, approaching negative 2. For your g function, when you go to negative infinity, your graph is actually going to negative infinity as well. When you're going towards positive infinity, if you're imagining that you could go to infinity and trace or drive on this graph to infinity, you would approach infinity as the height of your graph as well. So what we're discovering here, when you look at a limit at infinity, what it's telling you is if you are going to have a horizontal or a slant type asymptote. It's telling you essentially your end behavior, meaning the two ends of your graph, what are happening to them as you go way out to the left and way out to the right, what happens at the right and left end. So some basic truths about rational functions. When a factor is canceled from the denominator, that is where a whole has occurred. So when you're able to cancel that out, a whole occurs there. And when you don't factor, so when you're not able to cancel out a factor from the denominator, that is where a vertical asymptote will occur. This is true for your rational functions. These are two main ideas that we're going to use quite a bit. So let's apply that now. Looking at the limit for this rational function, because it's rational, we want to try to factor before we begin plugging in any values. We're looking at finding the limit as you approach 4 from the left. And in the numerator, you can factor out a 2. And then you're left with a little bit simpler quadratic function there in both the numerator and the denominator. And both the numerator and denominator, those quadratics can be factored into x plus 3 and x minus 2 in the numerator and x minus 4 and x minus 2 in the denominator. Now, they both have a common factor which we can cancel out. That is going to create a whole at the x value of 2. And we're left with this simpler rational function. And we're trying to find the limit as we approach 4 from the left. So if we select a value just to the left of that, say 3.9, and we plug that in, we don't really want to know what the value is there. What we're trying to figure out is what is happening here at, well, it's going to be our asymptote. If you see that denominator x minus 4, that means that there's going to be a vertical asymptote at 4. But coming from the left, are we going to infinity or are we going to negative infinity? The numerator, you're going to have a negative because you'll take a positive sum and multiply it by a negative. And 3.9 minus 4 results also in a negative. Negative over negative is going to result in a positive value, which means coming from the left of 4, the limit is going towards infinity. Now, same scenario, but coming from the right. We're looking at our simpler function. We know that really at 4 there is a vertical asymptote. But if we select a value just to the right of that, that would be 4.1. And we plug that in, you're going to have a negative value on top because it's going to be positive sum times a negative. But 4.1 minus 4, that's going to be a positive value. So you're going to have your limit here coming from that right-hand side is going to negative infinity. So now we were able to find our limits analytically there. I want you all to try C and D and see what kind of limits occur there. What are the infinite limits? Are they positive or are they negative? Do so in the same fashion as A and B in this example. I want to kind of analyze the two cases here in a nice little graphic organizer. If you have, let's look at case 1. When you have a non-zero factor over a zero factor, you're working with vertical asymptotes. And if you have 0 over 0, you're working with the location of a hole. Now, that was kind of maybe a little bit strange jargon, but let's put it into some of our more familiar calculus language. If the limit from the left goes to positive or negative infinity, or the limit from the right is going to positive or negative infinity, then that value that you're approaching, that a value, is a vertical asymptote. Let's use these ideas in our third example. This function below, we're going to find any vertical asymptotes, and we'll justify our answers using limits. Where do vertical asymptotes occur? They occur when factors are not able to be canceled from the denominator. So first we need to factor. If you factor the numerator, it would be 2x minus 1 and x plus 5, and the denominator is going to be factored to x minus 2 times x plus 5. And you can see that they have a common factor that we are able to cancel out. A hole will occur at that value at negative 5. And it would seem as though we're going to have a vertical asymptote at 2. But now let's justify that using limits, using the definition of a vertical asymptote, the limit definition, that is. The limit from the left, well, if we plug in a value just left of 2, that would be 1.9, and in the numerator that'll result in a positive, whereas in the denominator it will be negative value, which means we're going to negative infinity. From the right, you're looking at plugging in a number just slightly larger than 2, which would be 2.1. And in the numerator, it'll still be positive, and in the denominator as well, which means we have another infinite limit. This is our justification because we were just explained that a vertical asymptote occurs if from the right or from the left you have an infinite limit, and we sure enough do. Really, when talking about end behavior, that's another concept in this lesson, there are only 4 outcomes. You could have a curve that is increasing without bound, like this parabolic shape here, and your limit as you go to infinity is infinity. Or you could have a curve that is decreasing without bound, like you see on the left-hand side here as you're going to negative infinity. It's also going to negative infinity. You could have a curve that is asymptotic to the x-axis, which means here, as you go to infinity, the tail, the end behavior here is that it is going to 0. It's getting closer and closer to 0. Or you could have a scenario where your curve is asymptotic to a horizontal line like the line y equals 3. That's what you're seeing here as you're going really either to positive or negative infinity. You're approaching some value, some y value there. So these are the different scenarios for your end behavior. It could be increasing positively or decreasing positively without any bounds, or you could be approaching having this asymptotic nature to the x-axis or to some other y value, some other horizontal line. I want to talk through a few rules when it comes to your horizontal asymptotes. This is really kind of an idea from pre-calculus, but we want to go through it thoroughly because it is essential. If the degree in your numerator is less than the degree in your denominator, meaning it's bottom heavy, then your limit is 0. Your horizontal asymptote is 0. If your degree in the numerator is the same as the degree of your denominator, so your powers are equal, then the limit is the ratio of the coefficients of the highest degree in the numerator and denominator. And if the degree of the numerator is greater than the degree of the denominator, so it's top heavy, the limit does not exist. These are some rules for horizontal asymptotes. And I'm going to go ahead and pause the video here and start another video so that it's not too long. So take a little break and look for part 2.